department head in aerospace engineering, and I am pleased to present to you our first speaker from aerospace engineering is participating in the Bagley College of Engineering Distinguished Lecture Series. Today we have the privilege of welcoming Professor Dan Inman from the University of Michigan to speak to you today. I've known Dan professionally for about 4 or 5 years, and we were debating last night, how we first crossed, how our paths first crossed. And but I knew shortly after meeting Dan that he would be a fantastic speaker here at MSU. I think you'll find that he's got some very unique qualities. An excellent speaker. And I couldn't quite put my finger on one of the things that I found best about his personality. Last night at dinner, Dr. Horstmeyer asked Dan what he thought his major accomplishment was for his career. And it was quite an interesting response, and I think it will resonate with many of you. And Dr. Inman said that he was most proud, his proudest accomplishment was his 61 PhD students. And that was quite interesting. And I found myself that I finally thought, oh, I've got my finger on it. That Dan, is a people person. He invests in his students, and from what I've seen here, he's been also very invested in many of us here on campus. Now, Dan is highly accomplished, as many of you know. He's been a prolific researcher, but he's also a very good person and a dynamic speaker. As I mentioned, he is currently the department chair at the University of Michigan in Aerospace Engineering, but he also hails from Michigan State. And so it's kind of an interesting dynamic. It's a little bit akin to Jim Newman being an alumnus of Ole Miss and on our faculty here. And so it's my distinct pleasure to introduce to you Professor Dan Inman. Thank you.
Well, thanks so much for taking the time to come and listen to an old man in a nice sunny afternoon, although I think it's supposed to rain, so that I try to make it rain when my lectures occur so that people come. So I have to brag about the University of Michigan first. It's part of what we do, right? So we were the first aerospace department, established in 1914. It's real, and we're the #1 public aero department according to U.S. News and World Report, which doesn't really mean much. It's just kind of a beauty contest sort of thing. Which I should have brought along was my curriculum from 1914. It's very interesting to read. It has 3 courses in propeller design, balloon courses, stuff like that. So it's interesting how the curriculum has evolved. So one of my interests in coming here was taking a look at your curriculum and seeing how to do that. So the only important thing on this slide is my email address. If you have questions after the lecture, because most students are shy and don't want to ask questions, you can email me and I'll give it to some graduate student who will answer you. So I would take a sort of short history of all these things called smart materials, multifunctional structures, and more lately metastructures. So smart materials sort of started out, I guess it kind of got its boom in the 80s, and they're really transducer materials. So if I had given a talk like this 40 years ago, I'd call it transducer materials. In fact, I may have given this talk 40 years ago, I'm not sure. So they really correspond to talking things about the piezoelectric effect, shape and reality effect, electrostrictive materials, ER/MR fluids, things like that. And in the late 70s, they got integrated into structures that became known as smart structures, adaptive structures, intelligent structures, active structures, all kinds of names like that. The best one was a German name, which is called Adaptatronics, I think that's what it's called. So basically combining these transducer-like materials in an integrated way to try to imitate essentially nature. So it was motivated by human performance, the idea that basically human beings respond to a stimulus with some action. So the idea was, could we make a structure like that that sensed its environment and responded to that environment in a positive way. So there were big dreams early on about imitating human performance using smart materials. Didn't go anywhere, really boiled down to, again, discussing these different types of transduction materials and how to integrate them into structural functions. So, and other functions, sensing and actuation, basically. Then, more recently, the idea of multifunctional structures came around. That concept was it had sort of a deeper integration of these materials. So structures that combine sensing, actuation, structural integrity, and other functions. And some of the early work there consisted of what were called self-healing structures or self-colored structures or combinations of functions integrated at the material level. So a lot of work was integration at the material level. And then some guys came along and looked at load-bearing antennas and load-bearing batteries as a way to reduce weight on jet fighters, integrating the antenna functions into the skin of the aircraft. So what is the concept of multifunctional structure? Well, we have a lot of functions that are important to aerospace and other structures. The structural integrity being the main one, of course. Then can we integrate sensing, actuating, energy harvesting, storage, telemetry, computing into the structure itself? And then how would we measure that? We would measure that in terms of performance it could do, which would enhance the structural capabilities. So the whole game boils down to, can you do that and not introduce a lot of stress concentrations and not introduce a lot more mass? So those get to be the constraints. We'll talk a little bit about that. So here's a sample of a multifunctional composite, layered composite. Other people look at it more at material level. So there's perhaps a wing spar with a flexible solar panel, lithium-ion battery, a printable circuit board, an actuation device, a sensing device, some composites, materials to hold it all together. So that's a concept, and we'll play around a little bit with that concept. Then, more recently, the idea of metastructures came along. And this is kind of wild. A metastructure, so what's a metamaterial? Metastructures grew out of the concept of metamaterials. And metamaterials, if you look it up on your favorite Wikipedia page or whatever, it's basically an engineered material that's constructed to have properties that we don't find in nature. Often defined in terms of optical and microwave applications, which is where they were first discovered. They talk about things like increased band gap and negative index of refraction. So metastructures kind of extends these concepts to low frequency vibration and other functionalities. So the history of metamaterials started in the 60s in the Soviet Union in this paper by a guy whose name I can never pronounce properly, so I won't even try, where he looked at negative values of permittivity and that sort of thing. And this little cartoon here at the bottom kind of tells you what's going on. So this is something you're probably familiar with from your freshman or sophomore physics courses. That's the index of refraction. So it turns out that if you have a positive index of refraction, then it looks like the light bends as it goes through. If you have index of refraction 1, it's straight. If you have a negative index of refraction, which you can create by messing with the molecules in the liquid, then you can get a sort of a cloaking idea in the sense that this device appears to be someplace it's not. And so that created a whole buzz on cloaking and other things. I'm not going to talk about that or know anything about that, but it's using that concept of a made-up material, which in this case is this special liquid down here, to create properties that you don't see in nature. So now, that's sort of the background and the history of where we are. So now I'm going to just walk you through a couple of examples of things we can do with these three concepts and try to show you that. So we're looking at a small UAV here, and what can we do with that? So a small UAV, not all UAVs are small UAVs or radio-controlled airplanes, if you want to look at it that way, have spars, but those that do, we can look at asking the question is, what impact would this sort of thinking have on this? And so the idea was the following. One, we could harvest energy, run some small electronics. We could integrate storage into that, and maybe we could do gust alleviation. So gust alleviation on small UAVs is a little bit of a problem because they can quickly go unstable if they get much of a gust. and we could look at damping vibrations. So the first work in this area was done by a colleague at the Naval Research Labs, Jim Thomas, and his colleague Kidwad, whose name I forgot at the moment, Sadiq Kidwad, I think. So they took this small UAV and they replaced the skin with this integrated battery. So the battery actually was load bearing. So it's not just gluing a battery on your wing, it's replacing the wing with load bearing battery. And they did some studies on that, fabricated it, did some strength of material types of tests, that sort of thing. And showed that perhaps you could have an advantage here in terms of weight reduction. Because instead of a skin plus a battery, you would have a battery which served as a skin. And that's sort of the basic concept. So we looked at that and said, well, can we create a self-charging structure? Meaning that these spars vibrate. In the best of conditions, they vibrate. So could we take that vibration, use the piezoelectric effect, which I didn't tell you what that is, but hopefully you know. If you don't, it just means it's a material that when you strain it, it emits a voltage or electric field. And when you apply an electric field to it, it emits a strain. So you can use it both as a sensor and an actuator. And so could we do that and capture this voltage and run it into a circuit and then dump it into a battery and therefore create a self-charging system. And in fact, we did that. So we used this Thin film battery made by Thin Corporation, which is pretty lightweight, has a pretty low voltage, low current charge cycle. And then we also looked at using flexible solar panels on top of the wing and dumping all this current into a small battery so that we could charge as we flew and maybe use that energy to do something. Well, immediately we run into some interesting problems, and the problem actually lies in circuit theory. So these two devices see an electrical load, and they have an optimum. So the optimums are here. So this is the load resistance that they see, and this is the power out. And you can see there's a clear optimum here. So solar power, that requires a load resistance of about 200, which means whatever you connect it to, which in this case a battery, needs to have about impedance of about 20 ohms. Unfortunately, the piezoelectric system needs to see about 3 orders of magnitude more than that. It needs to be about 10 to the 4th ohm. So some electrical engineering problems, which I won't discuss, I just wanted to point out the problems. We built this spar-like structure that we could imitate in the lab to see if we could actually do this. We built a model of it, which includes all the extra dynamics of the 2 layers, and tested it and got a nice fix. So now, what can we do with that? So the last thing we want to do is introduce a penalty. So if we're taking energy out of the system, we don't want to penalize it. If we're adding mass, we don't want to penalize it. So really what we want to look at is what can we do to use this to an advantage in a flight situation. So when you design an aircraft spar, you're using the spar to reduce the opportunity for flutter. You want to hold the load up, you want to not have aerodynamic flutter instilled. So you make it really stiff. So we got the idea of what if we made it less stiff, added these other things and added a control system so that we could not experience the gust that would destroy the aircraft. And then we thought that was a kind of a stupid idea, but then we found out that the X-56A by Lockheed Martin does exactly that. They reduced the wing mass and added a flutter control suppression system. So it's not such a crazy idea. Not that I'm opposed to crazy ideas, that's why we became professors, right? So we chased that down. So we looked at adding the control system for gust alleviation to our energy harvesting system. Well, so here's the system. We have, that's our model airplane, or our radio controlled airplane. There's our circuit. We're not going to talk about the solar panel aspect here, just the piezoelectric aspect and the circuit board that goes with it. This is just a dynamic analysis of that system. And so the idea is the following. Can we take this harvested energy and use it to control vibration in aircraft. So it sounds like sort of like perpetual motion or anti-perpetual motion. But it turns out that you get very little energy that you can harvest. So you can't really use it directly. So you have to store it and then use it when the gust comes along. So that's sort of the game we're playing. We have all these components. Don't worry about that for now. The electronics layer, the battery layer, the spar. We have a harvesting piezoelectric, actuation piezoelectric, and a sensing piezoelectric. And actually we can combine two of those, so we don't have to have both of them, but that's sort of the schematic. So now the question is, we have a little bit of energy, we need to store it. Even after we store it, we still have a little bit of energy. So what kind of control system can we have that would allow us to use that energy and yet control the vibration induced by a gust? And so I searched the controls literature and didn't find anything. We have any controls people in here? Couple? I'll only lie a little bit. Okay. So we looked around. You could use LQR, LQG, and weight the matrix for the gain for the control input matrix. You could play around with that. That turns out not to be the optimal. It turns out to give us an optimal response is this crazy idea that we use a saturation function. So when you try to, if you look at vibration suppression, the controller looks at where the system is and looks at where it wants to be, and it applies energy to move the structure to that 0 point. So when it's far away from its 0, it calls for a lot of energy. And so all we're doing here is we're saying, let's not call for a lot of energy up front. Let's restrict the energy that we put into it early on when it's far away from 0, and then drive it down gradually. So we did that, and then we compared that to a bunch of different control laws. Compared it. So here we have, it's just a free response. So we have an initial condition here, velocity and position, and we have a bunch of different control laws that we're using. One is just open loop, so it takes about 9.5 seconds to die out, and we're going to compare ourselves to that. And we're going to design each of these controllers so that they have the same, roughly the same settling time, 4 seconds. And so we tweak those controllers, each of those controllers at 4 seconds, and then we measure how much energy it takes to get there. And look, when we do this choppy, we call it bang bang initially, but we got rid of that because that means something specifically different in controls literature. But by using that chirping control, we're able to get the same settling time for an order of magnitude less energy. So we had nonlinear controller, which is just a product of state feedback, and PPF controller is called positive position feedback. It's very positive, or very popular in structural control. It's really a second order filter is essentially what it is. It measures the feedback and then applies force. So what does that look like? So here's the control voltage input, and this is the difference between the two control laws. One causes for a lot of energy up front and then slowly dies out. The other one just chips it. So by 0.4 seconds, we're actually back to just using the linear controller, and we get an order of magnitude less energy consumption. So okay, I'm missing something here. I don't know what happened. Interesting. Okay, well, there's some nice plots there. Use your imagination, close your eyes, but don't close it too long. Basically, we couldn't fly anything at that time, and so we wanted to theoretically see if we were going to get anything. So we used Dryden's power spectral density to imitate our fluid mechanics, basically, or aerodynamics, and looked at clear sky versus a gust, and the Dryden power spectral density. If you don't know about that, you can find it in a lot of books, but basically depends on trim velocity, the length of the turbulence, and the root mean square value of the vertical gust. So all these plots showed up. Get nervous there for a minute. So here's what it looks like in terms of a couple of different gusts we modeled that will apply to this model. Here is well, let's just focus on this bottom plot here. So this is the spar undergoing a gust, blue. And this is the spar undergoing the same gust with the control system on. You can see it's much smaller amplitude, and that we've effectively controlled the system using this reduced energy control law. So does it work? Well, it's one of those great answers. It depends. Depends on the length of the gust, depends on how long you have to harvest, etc. So we looked up some cute little formulas to tell you exactly how to compute that. So this is the time it takes to harvest versus the total energy required divided by the harvested energy. And basically, if you apply that to different gusts, it says, in this particular case, for this particular model, if we can harvest 40 seconds, 40 times longer than the gust, so gust lasts for a second, if we can harvest 40 seconds before that, then we can control it. If we had a second gust before 40 seconds is up, nothing happens. So it kind of works. It's not a panacea, but it will get you by the first gust. And it all depends, again, upon how long you've been flying, and lots of variables. But it does do something. So now I'll move from that to the next example. So that's an example of a multifunctional structure that combines energy harvesting, control, sensing, and that sort of thing. So the next thing is metastructure. So what's a metastructure? Well, the first couple of good papers in this were by Massimo Rosini, Georgia Tech, a little school down the road here. Maybe you've heard of it. We try not to talk about it in Michigan because of the two public aerospace departments. They're our biggest competition in terms of rankings. But we know we're much better. So essentially what he did is he created this structure where we have lots of inserts, and these inserts really act like vibration absorbers and create sort of a broadband vibration absorption. Here's a plot. This is again taken from his papers of different structures. So this is a magnitude plot. I hope you're familiar with that. Is everybody familiar with the magnitude plot? I can suggest a really good book to read called Engineering Vibrations. I can't remember the author. Really handsome chap. You could study and learn about this. So basically, this is the frequency, and this is the amplitude. So high peaks. This is the plane frame without any of this stuff inside. You see there's some pretty high peaks. And then if we use this metastructure design, we see that we both reduce the peaks and spread them out a little bit. And so that's the idea of a metastructure. It's really, I found it pretty clever and pretty interesting. And then I looked at it and I said, well, really, this is just a bunch of vibration absorbers. So here's a structure with a bunch of vibration absorbers. And this is what we call a band gap, where nothing's happening in this region of frequency versus the amplitude. So we came up with a way to do this in a more unique way. One of the problems of this is getting low frequency and getting high bandwidth. So if you look at making tiny inserts to put in a large beam, then these things become small. And if they become small, and if you remember anything about vibration, if you look at just a basic cantilever beam, the frequency of oscillation, the fundamental frequency, is proportional to 1 over the 3/2 power of the length of that beam. So that means that if we try to make these little beams, little vibration absorbers, smaller and smaller and smaller, their frequency goes way up. In fact, it goes way up out of the bandwidth of anything we could call vibration. So that's kind of a problem. So we decided to solve it using this zigzag design and using a magnetic field to make the system nonlinear. So we looked at two different ways to get away from this length dependence. One is by making a spiral, and one is by making a zigzag design. We settled in on a zigzag design because it was easier to paint with piezoelectric materials, and at some point we wanted to make this active. So here's the 3/2 dependence I talked about. So as you shrink a cantilever, the frequency goes way up, approaches the kilohertz range, which isn't very good. There's a ton of work, previous work done by other researchers trying to reduce the frequency of a cantilever beam. So here was the first attempt in 2004, where they took a small beam and they made a big mass on the end. It got down to 3 kilohertz. It's pretty high. Then another group came along and tried to make a real lightweight system, and they went the wrong direction. They went with 3 kilohertz. Then another group came along, got it down to using a spiral design, got it down to 1.4 kilohertz. Then this guy came up with a 10 kilohertz version. This guy came up with a 1 kilohertz version, so they're getting there. Then somebody came along with large tip mass. Well, it's the square root of K over M, right? So if we make M large, so they came up with this design, which is totally ridiculous. Anybody who knows anything about it, these are double E's, so you can't help, right? Sorry about that. They can't help themselves, right? So they made this really large mass, this real thin composite, and that broke right away, of course, as you'd expect. A couple other people went down that path, trying to make large mass, but they're at least getting down into the vibration range of hertz instead of kilohertz. Then Lee et al. Came up with this design, which used that earlier design, put a tip mass on it. The material was again, kind of flimsy. Then this guy came up with a really crazy idea of having all kinds of little cantilevers coupled together. That was actually pretty clever, but not particularly easy to manufacture. So we came up with this zigzag design, and we could cut this. This is less than a millimeter in size. This is probably a couple of centimeters. We can do this with a laser cutting piece of aluminum, whatever. And then we added some tip mass if we wanted. And that turned out to do the job. So we had a little fun modeling it. I didn't want to give you the models because you can just read them and they take up pages. But basically we had governing equations. We had 6 unknowns per member. Each member looks like that. We have n members, 6 n unknown coefficients, 3 essential boundary conditions, 3 natural boundary conditions, so 6 total. And then we can solve using equilibrium and continuity. We can solve that system. We did that, and we got plots like this. So what does this plot say? This plot is the number of cuts this way. So if you take my beam and I cut it in a serrated fashion, make this zigzag shape, then that's n here. So that's the number of cuts. And this is frequency, which is kind of normalized to give you an idea. The idea here is, look, this is an order of magnitude. Okay, we're dropping orders of magnitude as we increase the number of cuts. Of course, at some point you'll reach saturation, you'll reach problems with fatigue and failure. But basically, by using that zigzag technique, you can get a real low frequency, small in a small space, real low frequency vibration absorber in a small space. So now we need to talk about the magnet. So we're going to put a magnet on the end and make this thing nonlinear. And here's kind of a cartoon which shows you again driving frequency versus, in this case, the magnitudes measured in volts to strain. And you can see this is the nonlinear curve. And of course, those of you who know anything about nonlinear dynamics, this goes on and then doubles back like that. So we just operate in that region. This is the linear one. And you see that except for these 2 points, the nonlinear one is broader band and higher. And then, so that gives us this broadband behavior where if the driving frequency shifts a little bit, we don't lose an order of magnitude in displacement or in voltage. Whereas for the linear case, it's not very broadband, it's peaky. We actually missed this point here. And if we want to match these amplitudes of the nonlinear system, we just need to go out a little farther. So that created a situation where we could actually get to limit cycle oscillations. You get a lot of strain in this device. Therefore, a lot of coupling between the piezoelectric effect, through the piezoelectric effect between the magnitude and the strain and the voltage. So here's a beam that we made out of those. These are blow-ups of these sections here. So the inside, you can see the side view here is a simple frame. And then here's a response. It's kind of an ugly plot made by an overzealous graduate student. All this stuff is made by graduate students, right? And we only hire overzealous ones and give reserve. But you can kind of see here a comparison between nothing, high amplitude, linear, okay? lower amplitude, but still very narrow band. And then nonlinear, we start to get this nonlinear wave. We start to get a broader band behavior and much lower frequency or lower amplitude. So the possibilities of this sort of thing are pretty awesome, because we can do the following. We have low frequency, high bandwidth vibration absorption. We could possibly use this for energy harvesting by painting the zigzag materials with piezoelectric material. And we've done that in another application. We've made it very small. We've made it the same size as a battery for a pacemaker. And we've shown that through tests on pigs at the medical school. I'm not talking about the faculty, I'm talking about the animal executive, that can power a pacemaker. So right now, you have to have, if you have a pacemaker, I don't, by the way, I don't want to experiment on myself. Usually you have to have it replaced every 7 to 10 years because the battery dies. And so it's a non-fun operation. It's not too bad because they've got it down to a real nice procedure, but still you have to do that. So if you put this device in it, assumably it would last perhaps forever. You wouldn't have to have those operations. But of course, there's a lot of federal, what's it called, FAA. I keep thinking FAA was worse than the FAA. What is it? FAA. Yeah, thank you. That a lot of tests that has to go through, and it's going to be a mess. It's going to be a long time. Pacemaker companies are not real happy about it because it means they won't sell a new pacemaker every 7 years. So it's not good for business from their perspective. So it's kind of caught in that mess. So that's one possibility. Active control is another possibility. Producing a multifunctional structure that's lighter, better absorption of the damping properties, and capable of sensing and actuating. The other really neat thing is that for a long time in bladed discs and turbine engines, there's been a vibration problem. And this happens at very high temperatures. So you could make these out of Inman, which means you could use them in a bladed disc application, which is something I've been trying to get Pratt & Whitney to pay attention to. They're almost as bad as FAAs. Okay, my third example, and everybody's favorite example because it's the last one. What time do you want me to quit, by the way?
Whenever you're done.
Whenever, okay. Well, I should have said that. Another 150 slides. No. I used to put down here in the corner, I tell my students, you should always put / how many slides you get so that the session chair can tell how close you're getting to the end. So as a joke, I used to put 1,000 down here. And my students started doing it. I said, it's not funny anymore. I don't want to miss lunch. So the next thing is to look at span line morphine trailing edge concept. So I was on a panel once with a guy named Paul McCready. I don't know if you know who he is, but he's deceased now. But he was a really fantastic aircraft designer. Designed a lot of really neat airplanes, human power airplanes. A lot of movies were made with his devices. Anyway, so a bunch of us got together at the Air Force Labs in Dayton and talked about designing a new aircraft, a new fighter plane. And so he brought, as part of his spiel, he brought a bunch of movies of birds doing a lot of things. So I was watching this movie and I noticed that when birds fly, they often move their feathers just a little bit. Sort of kind of like that. Now they have some, I don't know, 18 muscles or something they can do that with. And I thought, I wonder why they do that. So I asked around, I asked a bunch of bird biologists. Nobody knew. So I thought, well, it's kind of cool. So I gave a graduate student this kind of cool idea. I said, why don't you see what happens in simulation if you feather a wing. Okay, so take our wing. We normally have a discrete control panel like that. And what if we did this instead? Would there be any advantage? So of course, being a good graduate student, he went out to find that advantage, right? Instead of looking to see if there was an advantage, he was going to create one, I'm sure. But anyway, it turned out we convinced ourselves that you got a better lift over drag ratio if you did that compared to using a flap. So we started out doing that. So the next thing was, how do we build it? So We've done some earlier work using macrofiber composite actuators, which you see a picture of here. And what these are, this is a piezoelectric sheet laid on a Kapton sheet, and then it's diced into fibers, very tiny fibers, so there'll be hundreds of fibers in a sheet like that, with a thing called interdigitated electrodes laid over the top of it, and then another Kapton layer. So it's a flexible material, yet it's a ceramic material, and it has good coupling. And they're really awesome actuators. They were invented in 2000 by a guy named Keith Wilkie at NASA Langley Research Center. And we've used a lot of them. We got the initial contract to characterize them, so you can buy these now from a place called Smart Materials Corporation in Germany. And if you go to their website, you see a bunch of data. It's from one of my graduate students in about 2005 or so. So we're going to use this to do morphing. So morphing refers to shape changing in general. Can be applied in aircraft in a bunch of different ways. We're going to look at it in terms of improving maneuverability and lift-over drag. So here is a device we made. So on the top, we're looking at this sideways. We have this piezo embedded macrofiber composite here and one here. In the middle, we have a hinge mechanism later to be replaced with a compliant mechanism, so that these can shift at the back like that. And then we put a charge one way on the bottom layer and a charge the opposite way the top layer, so the top layer tries to stretch, the bottom layer tries to contract, and we can get some pretty good motion out of that. So this is kind of a cartoon of what happens. Here's the leading edge. And then these piezoelectric materials are going to create a force to move it up and down like that. And then here is a picture. And you can see that, you know, for a piezoelectric material which only has a few percent strain, we're getting quite a bit of deflection out of that device. And it's because essentially we've levered it. So if you remember back to your statics class, you remember that far back? I took statics 45 years ago. So I'm glad I can remember that. We can see we get quite a bit of deflection. And here it is in the wind tunnel. So if you look at it here, this is a solid state flat essentially. No moving parts really. No motor, just completely piezoelectric, holding an air load. And then we did that. We made an airplane out of it, where all the control surfaces on the airplane, tail, rudder, and the wings were all piezoelectric materials, completely solid state, and we flew it. It's a Nova episode called Making Things Smart. If you Google that, you'll find it. It's a pretty funny video, actually. So then we thought, so we flew that airplane, but we had all these materials, piezoelectric materials, were acting in unison. So now we want to make them act separately, so we can get that kind of feathering action. And of course, one of the problems we had to solve was skin. So we made two devices. One is going to be piezoelectric driven with a skin folder on top, so we get kind of a smooth, distributed motion. And then we're going to compare that to a similar wing with that many actuators on it. So here's a development of that device. Here we're fooling around with the skin, different skins. Here's the compliant mechanism that replaces that hinge. Owner Billion, who interviewed here 3 years ago.
Yeah, I think that's right.
He did the initial work on this wing, and then we're extending that concept by making these independent. Here's sort of the development of that. Using 3D printing or additive manufacturing is the fancy word. We could create a bunch of different scenarios for making this hinge. This is really critical. It didn't seem so critical, but basically we can't have any torsion on this. So we have to a little bit of a design optimization problem there. Then we had to deal with the skin. Again, we used the 3D printing to create a nice skin. We put honeycomb on one side and a smooth surface on the other side, so that we could get a skin that wouldn't flap in the breeze, so to speak, or flutter. Wouldn't be so stiff that it reduced our actuation ability. So we're trying to move two things opposed to each other, right? So the skin in the middle can't fight that too much, but at the same time, it can't be so flexible that it flutters or bubbles. So we did that. So the next thing we did was, well, piezoelectricity is very low strain, but very fast, which is good. If you're going to run an aircraft, you want it to be able to react quickly. The shape memory alloy effect is very slow, but it has high strain. So we thought, what happens if we combine these two devices? So we decided to do that. So we took this MFC thing that we had earlier, and we put inside of it a couple of piezoelectric wires and made this device, which you see here. And I think these all run at once, so I'm going to tell you what's going on. So one of these is just the macrofiber composite itself. These wires that you see are not the shape memory alloy wires. They're actually sensors and electronics. And then one of them is both together. One is shape memory alloy by itself, and one is piezoelectric material by itself. Oops. I'm supposed to go back to play this. There we go. Okay. So you can see the SMA and the shape memory alloy, and sorry, the piezoelectric material. Let me run it again. It's supposed to continuously run. I have to fire somebody over that. So basically, both together we get quite a nice response. It can both be fast, not as fast as piezoelectric by itself, and have high deflection, not as high a deflection as shape memory alloy, but something in between. Then we discovered we got this really cool shape, which you'll see here, this change in reflex here. And that gives us a really fantastic aerodynamic advantage. We haven't yet been able to combine this in a wing. This is relatively new. And I can happy to report that I think I just got a grant to do that. So I'm kind of excited about it. So here's, again, I showed this earlier, two devices we're going to compare. And here they are in the wind tunnel. So here's our distributed control system. You can see we get that serrated shape. Here it is the wind tunnel with the discrete version. And we're making comparisons between those now. And we're not done. So what? So basically, it kind of goes like this. Is this a good thing to do? Try to integrate these smart materials into a wing and use those instead of a traditional flap actuation device. So that's a very hard comparison to make because you're comparing completely two different things. You're comparing electric motors to piezoelectric materials. So you have weights associated with both. You have different electronics associated with both. But a company named Avid Corporation, which makes aerospace products, pretty small company, maybe 20, 30 employees, they got a contract from the Air Force to compare these, and they did that in 2012. They compared owner's original device to a particular wing, and what they found was it was heavier, which is a surprise, had better lift-to-drag ratio, not a surprise, comparable power consumption, and greatly increased bandwidth, and that's because the piezoelectrics are much faster than electric motor. Not a complete comparison, but a good start. And so other people now are trying to make comparisons. And this is how you have to sell technology. So you get a great idea, you make it work in a laboratory, and then you got to convince somebody who makes airplanes to use it. So everybody's favorite slide, it's called the last slide, or the summary slide. So what I hope I did was illustrate the utility of adaptive structures, multifunctional structures, and metastructures by a few examples. This sort of approach could lead to lighter, higher performance structural systems. And that's sort of what you want to do. You want to have a crazy idea, you want to try it out, and then you have to go and compare it to existing technologies to see if it was really worth anything in the first place. And then one of the roadblocks here that I see is now unpick the electrical engineers in the audience. One of the roadblocks here is really being able to embed electronics into a structure. So, there are flexible electronics, organic electronics. So all these things are really key. So if you want to go in this direction, especially for the morphine, I think And vibration suppression, I think it's good to team up with a double E who knows about these new technologies. So modeling and design those electronics, I think, is if you Google, or if you use Google Scholar and Google mechanics of flexible electronics, you find one paper, for instance, by a guy, colleague of mine at Harvard. So it's kind of an interesting area. And the future for improved structures may well lie in sorting out the integration of computing and power within a structural concept. And I think that's good if you're looking for areas to go. And I lied, it's not the last slide. I have to pay homage to my sponsors and, of course, to the many students who did all this work. All right, so they're listed here. My current students are Brittany and Katie. And previous students are Alex Pankadian, who we nicknamed Pokemon, of course. Jared Hoback, Steve Anton, Ya Wang, owner, Min Karami, Albert Urtak, John Ohayan, and Casio. So Casio and John are at companies, and everybody else is at a university. I like to create university professors. I don't know why they become my competition. What I should do is create program managers. That would be smart. So my favorite sugar daddy is Leslie at FOSR. It's fun. Most of what's the software. And with that, I'll open the floor to questions. It's hard for me to speak from a podium because I'm kind of a pacer. So.
Questions for Dr. Inman.
When you lower the frequency of those cantilever beams with the zigzag shape, is that more due to the actual geometry of the zigzag, or
it is
by the fact that you're lengthening the bar essentially?
You would think it would be a lengthening function, but it's really not. It's a dynamic mechanics issue. So you don't see it until you work out all the equations. But it's not so much lengthening the bar. There may be certainly an effect to that, but it's really the geometry of the zigzag, the way it vibrates, it couples torsion and bending. So there's not a clean answer to that question. It's a political answer. I can run for public office now because I didn't answer it. Other questions that I can't answer? Yes.
I'm curious, in the final applications that you showed where you had the conformal trailing edge, what you had made a point that the skin is still a pretty significant challenge, but one of the pictures you showed, you did have a skin that covered.
We did make a skin. We spent a bit of time trying to sort out the skin. There are a couple other people who have sorted out skins for morphing, Next Gen Corporation, Flexus Corporation, and nobody will share their technology.
Would you share?
I'd just like to buy a skin.
Yes.
But so we made this one with a honeycomb, which kind of gave us stiffness in one direction and a little flexibility at the same time. Yes, Chuck?
Yeah, have you ever done computational fluid dynamics on all of these structures and then the
Yes.
predictions?
So we have.
Does that work? Does the predictions
Yes.
work out similar?
Yeah. So we started by doing that. We have a young assistant professor in our group named Karthik Durasme, who has a couple of cheat codes that he's written himself for fooling the fluid, not doing full-out computational fluid mechanics, but vortex lattice method, stuff like that. So it doesn't capture all the effects, but captures, we felt, enough of it to make us feel good. So we have that part of the project as well. Other comments? I can't see.
Yeah, thank you so much for a fantastic presentation. University of Michigan.
Thank you.
I was just wondering, first question I have is with respect to your skin and the design you had. How did you ensure the interfacial adhesion between your physiologic material
The skin?
and the skin?
Yeah, we didn't spend a whole lot of time on that. We used the glue, of course, and we didn't have any trouble in our wind tunnel test, so we just accepted it. But I would say that's probably a good materials aspect to look at, is the adhesion between these different layers. And in the end, we try to cover it all with one skin, one thin polyurethane sort of skin.
Also, for bringing down your frequency, you looked at different flow patterns.
Yeah.
fuel cell we use interdigitated design, serpentine
Right.
flow pattern. So have you looked at, if you go back, look at the interdigitated one or serpentine or parallel, different design to create your material?
We only, you're talking about the zigzag?
Yeah.
We only looked at the zigzag and the spiral.
So you
Yeah.
look at serpentine type.
And we didn't look at a continuous serpentine type. We could very well do that. Mechanics was easier to work out for the zigzag. So we did that. It was his student's first project, and he got a really good model and he got a good fit with data. So we went with that. But there's quite a few other things you could try. And maybe the really cool thing to try would be some kind of optimization, topology optimization of that shape. But we didn't go down that path.
Lastly, I
It's
want
another PhD problem, see?
Yeah.
These kids are all going to get great PhDs.
As you know, the energy density of the smart material is a big issue.
Yes.
If you look into see how you in effect can enhance that energy density. And the energy density that you were showing us, is this gravimetric density or volumetric density? Volumetric energy or gravimetric energy?
It's volume, I believe it's volumetric. That plot was stolen from somebody else. We do that right. So I think it's volumetric. And to answer your question about are we worried about that? Sure, but I'm not a material scientist and I don't, I just want somebody else to do that. The best thing that we did was to use these macrofiber composites because if you look at piezoelectric material, it has 3 or 6, it's a tensor, so it has all these different components. So the D31 coefficient, which is what normal piezoelectric material uses, is about 1/3 of the size as the D33 coupling coefficient. And this interdigitated electrical pattern allows you to use that D33 coupling coefficient. So not at the material level, but at the design level, it's more efficient than a comparable monolithic piezoelectric material, just because of that interlacing of the fibers and the electric field.
Finally, I'd like to ask another question about, as you know, the graphene sheet is a hot item in the
Yes.
market right now. And so have you looked into seeing, because you can create beautiful baby now with respect to the graphene sheet.
Yeah, we have not looked into that. This guy's full of PhD topics.
Okay, thank you so much.
Thank you.
Other questions for Dr. Inman?
Well, remember my email anyway. Yes.
So in the, again, in the application with the conformal trailing edge, did you consider using the piezoelectric trailing edge to also harvest energy?
We have not. That would be sort of like that flag stuff that you talked about.
Right.
There's my former student at Cornell, one who just passed away. He was looking at that sort of thing. So if you search under Garcia energy harvesting, you might find some of that work.
Yes, sir. You said that your model was heavier than the other associated one. Do you know how much it was in?
I don't. I can send you the paper where I can look it up and.
I mean, look, I guess what I'm asking is. would
Yeah,
it
no,
make
it's
any
not far
difference?
off. It's not far off at all. It's not like an order of magnitude or twice even.
Okay.
Just one additional question. So I'm curious, in the application that you showed about gust alleviation using the piezoelectrics, which was in the initial part of your talk, I'm curious just that when you're actually extracting energy from the piezoelectrics, you basically, wouldn't that also act as a
It
as
does.
a
We have
damper?
a million papers, of course, right? So we have a paper that talks just about the damping caused by energy harvesting. And if you look at, for instance, we did it in a wind tunnel in Brazil because it was winter, and Brazil was a fun place to go. It's the other thing about being a faculty member, right? You get to go to fun places. So what we did was we measured the flutter speed, both with and without energy harvesting, and showed that you increased the flutter speed by a few percent. because of the damping that you added to the system by harvesting energy. But, having said that, there are two different optimums. So if you design a system to do energy harvesting versus one to do vibration suppression or added damping, the optimums are different. So you don't get to have the optimal system.
Okay.
One of it's going to be less optimal.
Okay, very good. Let's, one more. Last one.
So when using a shape memory alloy actuator, there's a martensitic to austenitic material transformation, and it's not always a smooth transition. Did you find when you were comparing controllers that phenomenon was hard to control, or that one controller did a subpar job of making a smooth transition between materials?
So we had an antagonistic pair. So that kind of helps smooth out that difficulty. And we also had the piezoelectric actuation over the top of it. So we did not see much of a problem with it. But it'd be something fun to investigate. Well, thank you very much. One more.
So the shape memory alloys versus the piezoelectrics, what is the relative difference in the power required to get the kind of output that you were interested in getting?
Okay. So I don't have a good answer for that. But I mean, we were using resistive heating, so that's a fairly inefficient process. And it does use more. I have a curve someplace that compares the power. I can't see it in my brain at the moment.
That's fine. Thank you, Bill.
Okay, very good. Let's thank Professor Inman.